on their way to map out our universe like never before and revolutionize space weather forecasting.
Stage separation confirmed.
NASA's SPHEREx mission tackles some of the most fundamental questions about the origins of water, galaxies, and the universe itself. The observatory combines two essential features that allow it to map the entire sky in a way that has never been done in astronomy before. First, the SPHEREx telescope has a wide field of view, so it can map the whole sky in a timely fashion. 22 full moons side by side could fit across a single SPHEREx image. The second key feature is the telescope's ability to observe in over 100 distinct colors at the same time. With previous telescopes, we had to choose between seeing a small slice of sky in many colors and an all-sky map in only a few colors. With SPHEREx, we can have both. Consider that our eyes are attuned to shades and combinations of just 3 primary colors of visible light: red, green, and blue. SPHEREx, on the other hand, sees the universe in over 100 distinct colors, in a type of light that's invisible to us, called infrared. Those colors are split amongst 6 different detectors, arranged in 2 groups of 3. Each detector group will see the same patch of sky in its respective color range. SPHEREx will need to scan the sky many times to build up a full spectral image. To see how this works, consider the galaxy in the middle of this image. Each time the SPHEREx detectors land on it, they will capture it in just 2 infrared colors. By shifting the position of the detector bit by bit, more color pairs will be filled in. Eventually, all of the detector arrays will need to pass over it to fill out their respective slices of the spectrum. After many repeated observations, the telescope will have filled in every part of the entire sky in over 100 colors. The colors help us understand what cosmic objects are made of and provide us with the information we need to make a 3D map of galaxies. This map will give us new clues about what happened to the universe immediately after the Big Bang, and help us identify frozen water, carbon dioxide, and other essential ingredients for life across our own galaxy. SPHEREx pushes the boundaries of technology to explore the unknown about our universe. Its observations will be a rich source of discoveries for many years to come. We call SPHEREx our small but mighty mission because it has some really ambitious science goals. The first is that we're trying to look back in time to see what happened in the first second after the Big Bang. We also want to understand how galaxies have evolved throughout history. And finally, we're looking for water and other basic ingredients for life in the places where stars and planets are forming.
BAE Systems partnered with JPL in the design and development of SPHEREx. BAE Systems was responsible for the integration and test of the spacecraft bus, which is everything below this metal ring you see around the center of the observatory. In addition, BAE Systems built the telescope that's at the center of the SPHEREx observatory.
The SPHEREx observatory is really 2 pieces. There's the bottom part that we call the spacecraft, and that's really the guts of the whole thing. It has the computer, the telecom system, the control system, the solar array on the backside, and then the top part is the payload. The payload consists of the telescope itself, the thing that takes the images.
The telescope is at the heart of how SPHEREx will observe the entire night sky.
And then these cones are thermal shields that help us keep the telescope cool.
The SPHEREx telescope and the detectors are required to be very temperature stable during their observations in order to collect that science data. And they lend this very distinctive structure to a spacecraft, one that I haven't seen before in my career.
SPHEREx has 3 cones, which are called photon shields. They block light and heat from the sun and the Earth. That's a big deal because without those shields, the telescope's detectors would be blinded. But SPHEREx also needs to be cold because it detects infrared light, or wavelengths slightly longer than what the human eye can see. Infrared is emitted by warm objects on Earth and out in the universe. It's also emitted by the telescope. Keeping it cold reduces the infrared glow, which lets SPHEREx see faint objects that are really, really far away. Here you can see one of SPHEREx's 3 cones being assembled. They sit atop this shiny jewel of a structure called a V-groove radiator. The mirrored surface directs heat out into space, cooling the telescope and the infrared detectors, cooling them to minus 350 degrees Fahrenheit. That is cold. SPHEREx can help us study everything from what happened a few seconds after the Big Bang to where water comes from in planetary systems. The V-groove radiator and the photon shields surround the heart of SPHEREx, the telescope. It's a feat of modern engineering, designed with incredible precision. And it looks tilted. That's not a mistake. That tilt helps it see the entire sky while under the protection of the photon shield. To understand the thermal avionics of SPHEREx, we must first address the harsh operational constraints of near-infrared space observation. Infrared detectors are essentially thermal sensors. They measure the heat energy emitted by cosmic objects. However, if the components of the telescope itself are warm, they emit their own infrared radiation, creating blinding thermal noise on the pixel arrays. To mitigate this, the payload must operate at extreme cryogenic temperatures, well below 100 Kelvin. Here, at the base of the optical assembly, we can observe the critical passive cooling infrastructure. Unlike missions that rely on finite liquid helium cryostats, SPHEREx utilizes a highly sustainable passive thermal design. Notice these prominent stacked aluminum structures. These are the specialized V-groove radiator rings, or chiller cones. They act as open-air thermal dump zones, progressively radiating structural heat away into the deep vacuum of space. As the crane lifts the payload, we get a clear view of the complex multi-zone sensor grid. Embedded within these thermal blankets are precise arrays of cryogenic resistance thermometers. These sensors transmit real-time telemetry back to the spacecraft bus, allowing the flight software to monitor micro-Kelvin temperature gradients across the structural interfaces. Managing this gradient is crucial. Uneven cooling causes material contraction, which would instantly misalign the mirror arrays. This rigorous testing confirms the absolute reliability of the passive design loop. By eliminating heavy mechanical coolers or boiling cryogens, SPHEREx dramatically reduces its launch mass while ensuring a stable, vibration-free environment for the focal plane arrays. The thermal telemetry analyzed here ensures that when SPHEREx scans the sky, it sees only the pure, unaltered infrared signature of interstellar glaciers, completely free from the thermal noise of its own machinery. What was the beginning of the universe like? Where did galaxies come from? And how did planets form from icy interstellar gas and dust? The SPHEREx mission will investigate all of these questions, with Caltech IPAC serving as a data processing and archival hub. Short for the Spectrophotometer for the History of the Universe, Epoch of Reionization, and ICE's Explorer, SPHEREx is a NASA Medium Explorer mission. It will provide the first all-sky spectral survey that will chart the cosmos in the near-infrared. What makes SPHEREx unique is its ability to cover the whole sky in 102 different channels of near-infrared light, enabling it to take a fingerprint of the universe. Assembled and tested at Caltech, the SPHEREx instrument is designed to explore 3 different cosmic origins. Shortly after the Big Bang, space rapidly expanded as it sowed the seeds for large-scale structures that would become galaxies today. SPHEREx will probe the early epoch of this inflation by measuring the 3D distribution of galaxies. How current galaxies evolved can be traced from the dawn of their light.
How current galaxies evolved can be traced from the dawn of their light. In between these galaxies lies a diffuse glow of distant objects that can't be individually observed. SPHEREx's sensitive map will examine its combined glow, known as extragalactic background light, and will help illuminate how stars and galaxies formed and evolved through cosmic time. Within galaxies, ice plays a role in the formation of stars and planets. By observing many sources across the whole sky, SPHEREx's wide spectral coverage can detect these ices and tease out molecules like water and carbon dioxide. During its 2-year primary mission, SPHEREx will deliver 4 massive fingerprint libraries of the entire sky.
SPHEREx does not navigate like a deep space probe. Its orbit was established during launch, and it has no propulsion system for routine orbit maintenance. Its main control challenge is maintaining precise and thermally safe telescope pointing while continuously surveying the sky. SPHEREx operates in a sun-synchronous low Earth orbit that follows approximately along Earth's day-night boundary, called the terminator. This geometry allows the fixed solar panel to remain illuminated while the telescope looks away from bright and warm objects. However, only a limited and continuously changing region of the sky is safe to observe. This region is called the Orbit-Varying Allowable Pointing Zone. During a survey sequence, SPHEREx stabilizes its pointing, records an exposure, and then moves by a small angular step to the next field. It continues observing one side of the allowable zone until that region is no longer safe or visible. The spacecraft then performs a much larger slew, sometimes as large as about 70 degrees, and continues the sequence on the opposite side.
To control its attitude, the spacecraft must first determine its exact orientation. A 2-headed star tracker compares observed stars with an onboard catalog and provides an absolute celestial reference. A hemispherical resonator gyro measures rotational motion between star tracker updates. Sun sensors and a magnetometer provide additional course attitude information, while GPS supplies orbital position and precise timing. Combining multiple sensors makes the attitude estimate more reliable than depending on only one instrument.
Actual pointing and slewing are performed by 4 reaction wheels. Changing a wheel's rotational speed produces an equal and opposite rotation of the spacecraft. The wheels are arranged in a tetrahedral configuration, providing redundancy. If one wheel becomes unavailable, SPHEREx can still maintain 3-axis control using the remaining 3 wheels, although maneuver performance is reduced. Because environmental torques gradually increase wheel momentum, 3 magnetic torque rods interact with Earth's magnetic field to unload the wheels, particularly during large slews and communication periods. Safety begins before commands are transmitted. Ground-based survey software rejects observations outside the permitted geometry and adds margins for orbit prediction errors, pointing uncertainty, thermal limits, and power requirements. The completed command sequence is independently checked. On board, autonomous fault protection applies even more conservative avoidance conditions. If no science target is currently safe, the planning system can select a safe location where the observatory waits until orbital motion opens another viewing region. This prevents direct illumination and excessive infrared stray light from the sun, Earth, or Moon from warming the telescope or contaminating its measurements. SPHEREx also passes through the South Atlantic anomaly, where energetic particles can cause detector transients. Although those images may still be transmitted, they are excluded when determining whether a region has received sufficient clean survey coverage. The final result is a carefully controlled rhythm of stabilization, exposure, small pointing steps, and larger safe slews. Repeating this sequence through thousands of orbits allows SPHEREx to revisit every region of the sky in 102 infrared wavelength bands, while preserving the cold and stable conditions required by its detectors.